All right, hello everyone. I'm going to start off by going over the test. Okay, we had, I had several copies that didn't have their names, and that took me time to assign those, and then I still have a couple copies that are illegible. Right. So we're waiting for a couple more people to join. Okay. All right, so I'm going to go over the test from last week. Right, so in the first compound here, our longest chain is 1, 2, 3, 4, 5, 6, 7. Okay, so that's heptane. Heptane. And the substituents are closer to the right side. Okay, so we'll start here. And this is a 2,3-dichloro-6-methyl. Dichloro-6-methyl heptane. And in terms of the configurations, okay, let's do each one separately here. We'll start at carbon number 2. Okay, chlorine is first, and then a carbon with a chlorine on it is second. Methyl is third, hydrogen is back. Okay, so this one is R. And number 3, okay, chlorine is 1. We have carbon and carbon, but the carbon with the chlorine would be 2, and the CH2 would be 3, and hydrogen is back. So that one is also R. So this is 2R, 3R. 2,3-dichloro-6-methyl heptane. All right, carbon number 6 is not a chiral center. We have two groups that are the same methyl groups. All right, moving over to the next one. Right, this is cyclopentane. And it's 1,3-dibromo. Okay, I would accept trans on this. Okay, we could start at either position. Okay, I'm going to start down. I'm going to start up here. Okay, so bromine is 1. Hydrogen is forward. Okay, we have a CH2 and a CH2. Those are the same. But we move on and we compare the next one over, the second one. And it's a CH2 versus a CHBr. Okay, so this one takes priority. So it's 1, 2, 3, like that, which looks counterclockwise, but it's but this is backwards. Hydrogen is coming toward you. Okay, so this one is actually R. Okay, so this is 1R. Let's check the other one. Okay, this is bromine is 1. Okay, and then the third carbon over here, this is these are the same, so this side has higher priority than that side, so it goes 1, 2, 3. Hydrogen is back, and so this one is also R. That's 1R, 3R, 1,3-dibromocyclopentane. Right, here our longest chain. It's 1, 2, 3, 4, 5, 6. Okay, so that's hexane. And with the double bond, it becomes hexene. Okay, so this is hex 2E. And we have a methyl group on 3. Okay, so this is 3-methyl. X2E. If you said 2-hexene, that would have also been acceptable. This is the more recent IUPAC method. And then in terms of configuration, okay, propyl takes priority over methyl. Okay, so this is the higher priority group. And then here we have a hydrogen, which is implied, and a methyl. Methyl takes priority. 2 higher groups are on opposite sides, so this one is E. All right, for this one, okay, our longest chain is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so there's a couple of different ways you could name this. Okay, as it's written, okay, that would be hexane. It would be 3-isopropyl hexane. And the configuration, okay, we've got an ethyl, a propyl, an isopropyl, and a hydrogen. Okay, the isopropyl is highest priority, then the propyl, then the ethyl. Okay, so this one is also R. So this is R, 3-isopropyl hexane. Okay, alternatively, you could have gone this way. Okay, 1, 2, 3, 4, 5, 6. And that would have been 2-methyl, 3-ethyl hexane. Okay, that would have also been acceptable. Okay, so here we have cyclopentane. 1-ethyl, 3-methyl. If you said cis, that would be acceptable. Okay, here we have CH2, CH2, CH2. Those are all the same. The ethyl would be lowest priority because the next one out is a carbon. Okay, so we compare these two, and then we compare these two, and then the one at the bottom has the higher priority. Okay, so that's 1, and then going this way it's 2, ethyl is 3. Okay, so that's R. And then down here, okay, this is CH2H, a methyl, 2CH2. So the methyl, okay, of these three groups, the methyl is the lowest priority. Okay, so these are the same, and then we compare CH2 versus CH ethyl. Okay, CH ethyl has the higher priority. All right, so we go. Okay, so we're comparing these two, we're comparing these two. So this is the higher priority, so it's 1, 2, 3. Okay, so this one is S. Okay. Okay, draw the correct structure, show the appropriate 3D structure. Okay, we have meso 2,3,4,5 tetrachlorohexane. Okay, a good way to show this, okay, would be a Fisher projection. Two, three, four, five. Tetrachloro. Okay, and there's actually more than one correct answer. Okay, we could have the chlorines on the other side. That would be the same thing. You could also show it this way. Both of these would have a plane of symmetry. Okay, or you could use the dashes and wedges. Okay, as long as you correctly showed that it was a molecule with a plane of symmetry. Okay, 1 chloro, 1 ethyl, 2 chloroethyl cyclopentane. All right, here's cyclopentane. All right, 1 chloro, 1 ethyl, and 2 chloroethyl. Okay, so this is position 1, this is position 2. Okay, this is an ethyl, and then we count from the point of attachment, so this is 2 chloroethyl. And there's a hydrogen here that's applied. And we want this to be 1R, 2S. Okay, so we could arbitrarily bring this chlorine forward and the ethyl back. Check it. If it's wrong, all we have to do is switch these two. Okay, so chlorine is first. Compare these two. The carbon with the substituents on it is second, and then the CH2 is third. So this is R. Okay, so that's 1R, and that is correct. Okay, and then this one, arbitrarily, I'll put the hydrogen back and the chloroethyl group forward. Okay, so we have a a CH2 and a CH2, and then we've got a carbon with a chlorine on it. Okay, so this would be number 1. Okay, we're comparing a CH2, and then it's a CH2, and the CH2 with the chlorine would have higher priority. Okay, so this side is 2, and then this is 3. Okay, so we go 1, 2, 3. Okay, that's not S, and so we have to switch these. Okay, so we'll put this one back and hydrogen forward. Now, that's 1R, 2S. Okay, in order to receive full credit, I have to be able to tell by looking at it that it's R or S. Okay, so we have 3-ethyl 2,3-dibromooctane. Okay, so this is octane, and then ethyl. Your 3-dibromo. 2,3-dibromo, sorry. Okay. 3-ethyl 2,3-dibromo. Okay, and again, we want 2S3R. Okay, so arbitrarily, start here. Okay, bromine is first. Carbon with the bromine on it is second. Methyl is third. That is R. And we want S, so we need to switch these. Okay, so let's bring hydrogen forward and bromine back. Okay, so now that is 2S. And then the next one, 3R. Okay, so I'm going to start out, I'll bring the bromine forward and the ethyl group back. Okay, so we have bromine, okay, carbon with the bromine on it is 2. Okay, this pentyl group is 3, and then ethyl is 4. So 1, 2, 3. So that one is R, which is what we're looking for. Okay, so this would be the correct configuration. All right, for the next one, we have E25-diiodo-3-hexene, or you could also say hex-3-ene. Okay, so here's hexane and hexene. We have a double bond between 3 and 4. And we have iodines at 2 and 5. Okay, and the way that I've drawn this, okay, that is E. Okay, just as a side note, if I wanted to show the Z, okay, all I would have to do is switch these. Okay, so I would bring the hydrogen up here and the iodoethyl group down here. So that would be Z. Okay, indicate the configuration R or S of the marked chiral centers. Right, so hydrogen's already back. We have a CH2. We have a tert-butyl group, and we've got an isopropyl group. Okay, a carbon with 3 carbons on it takes priority over a carbon with 2 carbons or a carbon with 1 carbon. Okay, so the tert-butyl is highest priority, then the isopropyl, and then this other group. Okay, so this goes counterclockwise, so this one is S. Okay, so here we have a Fisher projection. By definition, vertical groups are back, horizontal groups are forward. Okay, so I'm going to draw this using a 3D perspective. Right, so the carboxylic acid group is back, and this hydrogen is forward. This amino group is forward. And then we have an ethyl group at the bottom. All right, both these chiral centers are marked. Okay, taking these one at a time. Okay, we have 4 different groups. We've got the carboxylic acid, the amino, the hydrogen, and this group down here. Right, nitrogen has a higher atomic number than carbon. Okay, so it's first, and hydrogen is last. Okay, here we have a carbon and a carbon. Okay, we've got 2 oxygens and a carbon, and we would count this as 3 oxygens. So the carboxylic acid group is higher priority. So this is 2, and then this group down at the bottom is 3. Okay, so this goes 1, 2, 3. It looks like it is counterclockwise, but notice the hydrogen is forward. Okay, so 1, 2, 3. So this is actually R. Right, and then carbon number 3 down here. We have carbon, carbon, oxygen, oxygen. Oxygen has a higher atomic number than carbon. Okay, these are the same. Ethyl wins out over methyl. Right, so this is the higher priority group. Right, this one would be second. And then carbon is third. And ethyl is last. Okay, so this goes 1, 2, 3, okay, which is clockwise, and the lowest priority group is back. So 1, 2, 3. So this one would also be R. Okay, question number 4. Okay, draw the enantiomers of both compounds. Okay, for the one on the left, we would switch any two groups. Okay, so for example, I can switch the isopropyl and the terbutyl. Okay, keep hydrogen back. Okay, so this is a possible answer for the enantiomer. Okay, you can switch any two groups and you've got the enantiomer. Okay, when you have a molecule with more than one chiral center, you have to switch the configuration at all of the chiral centers. Okay, so this is the original molecule, carboxylic acid. Okay, so this is the enantiomer. Okay, if we were to switch just one chiral center but not the other, that would be a diastereomer. Okay. All right. The molecules in question 3 were just ones that I made up. The one in question number 5, this was actually one that one of my research students made a few years ago. Okay, so 2 diastereomers of the following compound. Okay, we have 3 chiral centers. Okay, we have this one at the ring juncture, we have this other one, and then we have this one down here. Okay, so there are 7 possible diastereomers here. No, I'm sorry. There's six possible diastereomers. There's one enantiomer, and then there'd be six diastereomers. Okay, so one possibility would be to keep this configuration the same. And then switch the configuration so that carboxylic acid is back and the hydrogen is forward. This. Okay, so that's one possibility. Okay, we could also, you could also make the ring trans. Okay, so we could have a trans configuration like this. Okay, so there's more than 2 correct answers for this one. All right, number 6, Brett's rule. Brett's rule says that for a small bridged bicyclic system, that is where all of the rings are smaller than 8 members, you cannot have a double bond at the bridge head. Okay, so this would be a violation of Brett's rule. Okay, this would also be a violation of Brett's rule if you have the double bond here. In fact, both those molecules are impossible. They're prohibitively strained. Okay, but if at least one of the rings has at least 8 members, then we can have a double bond at the bridge head. Right, if one of the bridges has 0 carbons, then it's perfectly okay to have the double bond at the bridge head. Okay, Zaitsev's rule. Okay, you could probably state this several different ways, but in an elimination reaction, the most stable alkene, which is the most substituted alkene, is the one that predominates. Okay, in the free radical bromination, okay, of this compound, using N-bromosuccinimide, one product predominates. Okay, so N-bromosuccinimide is a reagent for generating bromine free radicals. Right, so if we abstract one of these hydrogens here, or at the equivalent position over here, we have a free radical which is both tertiary and allylic. Okay, it's stabilized by resonance with the double bond. Okay, and then so during a termination or propagation step, all right, this would be the predominant product. Okay, a vinyl radical, okay, one actually right at the double bond is actually pretty unstable, and then a primary free radical is not stable either. Okay, so this would go through a free radical which is both tertiary and allylic. All right, SN2. Okay, so sodium is a spectator, just ignore it. Right, so a bond is formed, a bond is broken at the same time. And so our product would be this ether. All right, the next one is also an SN2. All right, again, sodium is a spectator. Sulfur is a nucleophilic atom. This will attack from the backside. And our product would have an inverted configuration at this chiral center. Okay, since the nucleophile has to attack from behind, it's going to push this hydrogen to the other side. Okay, and that's the same way with the third example. In cyanide, carbon is the nucleophilic atom. So this will come in from behind. And that will push the hydrogen forward. Okay, the next one is an SN1. All right, so the first step is dissociation or heterolysis. Chlorine leaves. Okay, that gives us a tertiary carbocation. Water comes in and attacks. All right, and then another water removes this hydrogen. Right, and then we get this alcohol, and my product would be hydronium. You didn't necessarily have to show the hydronium, as long as you showed the organic product. Okay, so number 10, show the E1 mechanism for that same reaction. Right, it starts out again with dissociation or heterolysis. Okay, and the question here specifies the major product. Okay, so we want the Zaitsev product. Doing this in water. Okay, so we have CH3, CH3, and CH2. Okay, removing one of these beta hydrogens would give you the most substituted product. Okay, so if we remove this hydrogen like that, all right, this would be the major product. Okay, partial credit if you showed a minor product. Okay, which would be this. Okay, so this is the major, this is the minor. No credit if you did an SN1 because the question specifies E1. Okay, then we have a couple of E2 reactions. Okay, so we want to look for the beta hydrogens. Okay, there's 2 here and 2 here. So this would remove a beta hydrogen, form the double bond, push out the bromine. Okay, and if you showed E or Z, either one, that would be fine. Okay, this happens to be the E isomer. Okay, and then we have a cyclohexane chair. Bromine down here. Right, this is an E2, so the hydrogen and the halogen have to be anti to each other. There is a beta hydrogen over here, but this hydrogen and this bromine are gauche to each other. They're not anti. Okay, so only this one could be removed. And we're using OCH3 minus. Take a hydrogen, form the double bond, we kick out the bromine, and our product is cyclohexene. Actually, 3-methyl cyclohexene. Okay, number 12, the pure R isomer of a compound has a rotation of negative 28.0 degrees. Okay, the pure S would have the same rotation but opposite sign, so it would be plus 28 degrees. Okay, a mixture has an observed rotation of 14. What is the enantiomeric excess or optical purity? Okay, so we would take 14 divided by the rotation of the pure enantiomer times 100%. Okay, so that gives us 50% enantiomeric excess. Okay, what are the percentages? Okay, since the observed rotation was positive, okay, that means that the excess would be for the S isomer. So there's a 50% excess. Okay, so we have 50% S, okay, plus the remaining 50% would be a racemic mixture. So we have 25% S and 25% R. Okay, so overall, we have 75% S and 25% R. Okay, a polar aprotic solvent is one that lacks an NH or OH. It still has a dipole moment. It's one that can accept hydrogen bonds but cannot donate them. Many examples, DMSO, acetone, ethyl ether. Okay, we're running out of time, so I'm going to skip over these nomenclature. Number 15, there were many examples of compounds that you could have cited that have different biological effects for their enantiomers. The Hammond postulate says that species that are similar in energy in a reaction diagram are similar in structure. All right, so for an endothermic reaction, the transition state would be closer in structure to the products, whereas in an exothermic reaction, the transition state would more resemble the reactants. All right, a racemic mixture is an equimolar mixture of two enantiomers. Okay, and we are, okay, so time is up, so I'm going to end there. Okay, we just about got finished, all except for these nomenclature questions. Okay, so I'm going to go ahead and end there. And I will see you on Monday.